So this Perl tries to answer a single question. What is a contract system? Usually, when we try to describe to someone what is a contract system, we present it as an extension to some sort of language. We add to the syntax, the C category up there, a few contract combinators that somehow we designed. And then we also extended reduction rules with rules that show how our language is going to calculate with these combinators. However, this approach is good enough if we want to get a grasp of how, what is the operational behavior of the combinators we have added to our language. At the same time, though, it obscures that a contract system is a very complex system consisting from distinct but interdependent parts. So what our answer is to what a contract system is a conceptual analysis that basically splits a contract system into its parts and then studies the relations between these parts. And in particular, today I'm going to talk to you about two pieces of a contract system, the interposition layer and the contract DSL. Before I get into details about what those pieces are exactly, I would like first to tell you why this is important. So, intuitively, those pieces define axes, and together those axes basically define a design space. By selecting one point in the contract DSL axis and one point in the interposition layer axis, we end up with a contract system. Racket, for instance, has made some selection in one axis and another selection in another axis, and we got the Racket contract system. But there are so many contract systems out there that we don't know about, and by considering the spectrum of choices we have here, we can come up with new ones, and some of them may be useful, far away from the one that Racket, for instance, has. So, okay, let's look at the two pieces. Let's look first at the interposition layer. It's a very useful and intuitive idea to look at the execution of a program as a sequence of events. Those events happen anytime the runtime of the language interacts with an entity from the runtime representation of the program. The interposition layer is the piece of the runtime of a language that allows the programmer to capture some of these events. When I'm talking about events, I mean a function application, a method call, an access to a ref cell, writing to a ref cell. So the interposition layer allows the programmer to notice that these events happen. And together with that, it allows to the programmer to learn more information from these events. For instance, for a function application, what are the arguments? What is the result? For a method invocation, what is the receiver object? For a REST cell access, what is the contents of this cell? There are many ways we can implement this kind of interposition systems, of interposition layers. The first one, and the easiest, is with code rewriting. It happens as a compilation phase. We know that from aspects. IFL also does the same thing to implement its contract system. So what happens is, at least in the case of IFL, that the programmer adds some directive as part of their code, and then during compilation, the compiler installs probes to be able to interpose at the necessary events and collect all the necessary information. This approach, though, has its limitations. Because it requires to recompile the whole code, it doesn't work really well when we are dealing with first-class values. For instance, if we only want to interpose when a closure is called in a given dynamic context. So the first way to get away from that is to use some sort of data expansion, and that's exactly what Racket was doing early on. But of course, this is not complete either. It's not a good solution because we don't only want to interpose on functions. There are other constructs in our language like vectors and boxes, and it will be good to be able to interpose in general terms. So in Racket and lately in JavaScript, the idea is that we have proxy objects, objects that wrap around any other entities, any other values like functions, ref cells, vectors, whatever, and anytime the runtime of the language interacts with those, we can configure the proxies to collect whatever information we want from this interaction. Of course, again, this is not the end. These are only extensional events, and there are plenty of events out there that existing interposition layers cannot capture. For instance, if you give me your closure, and you pass it as an argument to my code, and I want to make sure that your closure is not going to use memory as much, the usage of memory it's going to do is going to be within a limit. We cannot do it with proxies. So there are a lot of events that may be useful for programmers to have access to that we don't know yet how to capture. And this is really important because the abilities of capturing events and information about them underpin the power of the second part of our analysis, the contract DSL. So what do I mean by a contract DSL? It's a collection of linguistic constructs that allows us to declare which points from the interposition layer we care about, what information available from the interposition layer about these points we care about, and then to state properties of this information, and as a result, state properties of the programs. So these constructs are also known as contract combinators, and they basically are the things that we use to build contracts. Okay, I want to walk you through some basic contract combinations, some canonical ones, the flat and the arrow contract, to try to explain this in concrete terms. This snippet shows, it's a racket snippet that basically says that the module that contains this snippet exports the value bound to name under the contract symbol question mark. The symbol question mark is one of the simplest contracts you can have in Racket. It's a flat contract that basically states that the value bound to name has to be a symbol. Now, in terms of the 3 points I showed you before, this contract, the symbol question mark, declares one point of interest. And this is the attachment moment of the contract to the value bound by name. Oh, sorry. It also declares one piece of information that we care about. And this is what exactly is the value bound by name. This is what we learn from the interposition system, the exact value bound by name. And finally, one property. Is this value a symbol? This kind of reasoning can scale when we look into the immediate next more complicated contract. This is the arrow contract. So here we have a function f exported from our module under the contract that says that the argument has to be a symbol and the result a number. Okay, we have 3 points of interest now. The attachment, just like before, but we also have every function application and every function return. And we have one piece of information per point. First, for the attachment, we have the value bound to f itself. For the application, we have the argument, and for the return of the function, we have the result. And we have a bunch of properties, one per point again. First, we have the property that f must be a procedure, and particularly a procedure of a given arity. Second, and third, we have properties that are described by the subcontracts of this arrow contract, particular properties of the arguments and the results for the uses of this function. Oh. Okay, and there is also another orthogonal idea that comes into this contract DSL piece of a contract system, that if our contract DSL is not just a set of combinators separate from the host language, separate from the language that we use to write the rest of the program, but the contract DSL is embedded shallowly inside our host language, then we get extra goodies. For instance, any programmer can define their own flat contracts by defining basically predicates, like they will do in the language. And they can define, they can write, these predicates can perform arbitrary computation, anything that they want, and they can use them to form complicated contracts. For instance, this one here is a predicate that checks if something is a representation of a closure, and also checks that all the arguments are, there are no free names inside this closure. The other thing we can do is, since contracts are ordinary values, we can compose them using contract combinators like we could compose ordinary values in our language and obtain much more complicated contracts gradually. And also, since contracts, again, are normal values in our language, we can name them. And by naming the contracts, we can use them in even more complicated contracts. And this way, we can give very concise and comprehensible descriptions of complex properties of values and programs. Okay, so we used the 3 points that I talked about to try to describe existing contracts, but the immediate next question is, how can this help us to design new contracts, to extend an existing contract system? And this is exactly what we're going to talk up next. And we are going to use as a running example the implementation of a card game called Take 5. So in Take 5, we have a dealer that hands out cards to players, and then the dealer can ask the players either to start a round, or to start a turn, or to do in each turn a secondary move called choose. Our implementation, by the way, is an object-oriented one, so we represent the dealer as an object, the players as objects that have the interface implied by the 3 messages they receive, and those messages correspond to methods. So as every game, every card game, there is a protocol that must be followed. Not all messages can be received in any possible order. So, for example, here, the dealer first has to send a message start round to the players at the beginning of the game. Then, after the dealer does that, then and only then the dealer can send a start turn message. And after the dealer sends the start turn message, then more possibilities open up. Either the dealer can ask the player to take another turn, or to perform the secondary move choose, or to start a new round again. So it will be great if we had a systematic way using our analysis to be able to capture this protocol with a contract and enforce it at runtime. Of course, as we say, the view of a contract system as a composite system of 2 pieces guide us to achieve a principled design of protocol contracts. How do we do that? Interposition layer. The first idea is that the contract system, the basic level of a contract system is the interposition layer that describes what events happen during the execution of a program. And the method call, as we've seen before, the method invocation is one of those events. So if we can capture the method invocation and learn what method is called at each point in the at each point during the game, then we're already halfway there. And of course, we can do that. There is already a contract combinator that allows us to capture method invocations on objects by basically wrapping those objects with the appropriate contract, in this particular case, object C. What we are missing now is a way to describe what are the allowed states at each point in the game. And we can easily do that by bundling inside our combinator, inside our proxy, a little bit of state that keeps track of what are the allowed calls, the allowed next methods that one can make at each given point in the game. So, and then if we have this information, if we know what are the allowed calls, we can state conformance with the protocol as a property that basically checks if the current method call we're about to perform is among the allowed calls. Of course, every time we perform a method call, we go and update the state so that we keep things up to date. So for instance, after we do start round, since the next allowed state becomes start turn, we have updated the little memory, the little store that we have bundled inside our proxy. Of course, if something goes wrong and we call a method out of order, the contract system is going to intervene and give us a really nice contract error that is going to describe precisely how we violated the protocol. So okay, this is okay, but basically we are asking the programmer, in order to implement these protocol contracts, to combine 2 seemingly orthogonal features of a programming language: object contracts with state. And this may look like a pretty challenging task for an ordinary programmer. But we have an answer to that. What is hard for the programmer is also a challenge and a call for the language designer to design an extension to their language. And exactly that's what we're going to do. We are going to package up this combination of state and object contracts in a little DSL to write protocol contracts. And in Racket, we can do that with the help of our best friend, macros, but this is not a Racket-specific thing. In any language that has a decent syntax transformation infrastructure, one can also do the same thing. So how does our DSL look? Basically, it allows us to state the protocols in the form of state transitions. We basically define a little automaton. So inside this protocol block, we are going to have the different pieces of the automaton definition. The first thing is the initial state. The initial state is the method, the first method that the dealer can call on a player object. In this case, it's start round. Then after, we have the transitions, the transition function of our automaton. And every case of the transition function, the left-hand side is one state. It's one method. It checks whether the method we are about to perform is one of the allowed methods. It's one included in the current state. The right-hand side is how we are going to update the state of the automaton. What are the next allowed methods after we successfully perform the call we're trying to do? And that's it. The programmer doesn't need to know anything about the implementation, about object contracts, about state. They have this declarative style of writing the automaton, and that's it. Then the automaton returns a function that every time it's called, it gives you back a fresh contract with its fresh state, and they can attach it to the player objects and export them and use them in the game. Okay, so far so good, but some of you may wonder that the protocol that I described is particularly simple. Of course, the game has much more complicated rules. One of those, for instance, says that the player should not perform any number of turns in a given round, but the number of turns a player should perform is bound by the number of cards given to the player at the beginning of the round by the dealer. So, can we do it? Yes, of course we can do it. It's a very simple extension as long as we are thinking about contracts in terms of the interposition layer and the contract DSL. All we need to think is that we need a little bit of more state inside our proxy. A state, a piece of a ref cell that is going to keep track of how many turns are left per player per round. Okay? And also, from the interposition layer, we have access to the arguments of method calls. So, after a message to start a round, we can update this information about how many turns are left and set it to the size of the list of cards that was given to the player at the beginning of the round. And every time a player performs a new turn, we can decrease the number of turns left and then check that it's always greater than 0. Okay? So again, our macros and our little DSL can help us describe this in a very concise way. All we need to do is to add to the existing features of our protocol DSL that our automaton now, except of the state, has also local registers. In this particular case, one local register called turn left that we initialize with the value 0. And then at any transition where this is applicable, we can add directives to check properties of the local register and also update the local register. For instance, when we start a turn, we check that there are some turns left, and we also reduce the number of turns left. And of course, again, if something goes wrong and we try to do one more turn than it's allowed, we're going to get a nice contract error that is going to describe what condition exactly failed. So I want to leave you with two thoughts. The first is an effort to generalize the usefulness, the validity of this analysis. So as I said before, we can view intuitively the contract DSL and the interposition layer as axes that define a design space. It can also help us, this view of the relation between the two axes, to compare existing contract systems by basically splitting them up into their pieces and comparing the individual pieces. The other thing we can do is also it can help us to combine, to compose existing contract systems by basically, again, splitting the contract systems into their pieces and take the union of the individual pieces. The last thing I would like to say is try to put this work into some sort of historical perspective. So what we have observed the last 15 years of research in higher order contracts has happened before, not in contracts, but with type systems and types. So in the 70s and then in the 80s, there was a big strand of research that was looking at the meaning of types. And there were many useful insights there, many great results. But in parallel with that, there was another strand of research in type systems that was looking at how programmers interact with a type system. Why they find it useful, how we can use these ideas about the pragmatic value of a type system to prove things that are useful about type systems, like progress and preservation, to program in the presence of type systems, like type programming, and to design new type systems. The same thing exactly is happening for the last 15 years with contracts. There is a strand of research that for a long time has been looking at the meaning of contracts. And there are a lot of ideas about what contracts mean. Some of them are inspired by types, some are not. It doesn't matter. But even though this strand of research has given us some insight, it hasn't let us design new contract systems. It hasn't let us understand how we program. What is the equivalent of the typeful programming? What is contractful programming, for instance? We don't know. And for that, and this is a call to all of you, the whole community of programming languages, we need to investigate the pragmatic of contract systems. Because only if we understand contract systems and their pragmatics, we'll be able to unleash their power and help programmers more. Thank you.
Okay, we have time for one quick question. Yes. And could you state your name and affiliation first?
Vasco Vasconcelos, University of Lisbon. I've got two small questions. One is, have you ever looked at the type states for object-oriented programming and session types for many other different...
Yes, of course.
So what's the relationship with this?
I mean, they are static, right? Type state and session types. I mean, there are also dynamic applications of those. Yes, they are close. It's another way to state this kind of protocol properties.
It is. Can these kind of systems describe a behavior such that the continuing computation depends on the result of a previous method?
Yes.
You can do this?
Yes.
Okay. With the
yes. If you combine session types with dynamic checking, I think the expressiveness, again, we are talking intuitively because there is no formal definition of the expressiveness of contract systems yet, right? And informally, we're talking informally. I think the expressiveness is comparable. And if contract systems are not more powerful because you can store as much information as you want.
Okay. So let's all thank Christos again.
Oh, thank you.